Welcome to ScienceCover.com. In this session, we will look at AC and DC current. We'll focus on what we mean by a DC current, what we mean by an AC current, and how we can use an oscilloscope to test those currents. First, pause the video and try the Do Now task, recalling the parts of the power station. Let's check our answer to the Do Now task. First, the coal is burned inside a furnace or a boiler. This will change the water into steam. The steam will spin a turbine. The turbine rotates a magnet inside the generator, and then the transformer increases the voltage. So the missing terms were boiler, turbine, generator, and transformer. Then we were asked to describe how a power station produces electricity. So first we should say that coal or fossil fuels are burned to produce heat. The heat is used to warm water into steam. The steam is used to spin a turbine. The steam cools and condenses back to water so it can be used again. The turbine spins a generator. The generator moves a coil over a magnet, producing electricity, and the voltage is increased at the transformer. Let us start by looking at what is meant by a DC current. A DC current is a direct current. If we think about a cell, it has two oppositely charged sides. We have a positive side and a negative side. So when we make this into a circuit, the electrons, which are negatively charged, are repelled by the negative side and pulled towards the positive side. This means that all of the electrons are flowing in the same direction continually. However, current is assumed to be positive, and so we treat it as if it flows the opposite way to the electrons. So this means for a conventional current, we treat it as flowing positive to negative all of the time. As there is no change in direction, we call this a direct current. Now pause the video and try task 1. Let's check our answers to task 1. First, we had to add arrows to the circuit to show the direction of current in the circuit. Now, despite the fact electrons will move from negative to positive, we treat current as being positive, and so current will move from positive to negative. So our arrows need to reflect that as shown on the diagram. Part B asks us to explain how the electrons will move in a DC circuit. So here we can explain that electrons are negatively charged, and they will therefore be repelled by the negative plate and pulled towards the positive plate. This means that electrons will actually flow from negative to positive. Now let's look at an AC current. An AC current is an alternating current. Means electricity is an alternating current. This is because it's produced at a power station where a magnet is moving past a coil. As the North Pole sweeps past the coil, electrons are forced to move inside the coil. This creates an electric current. Maximum current is produced when the magnet is at 90 degrees to the coil. Once it's past this point, the current is reduced. And if the magnet is parallel to the coil, then no current is produced. As the South Pole moves past the coil, the current is forced in the opposite direction. This is because the South Pole has the opposite charge to the North Pole. Again, the current is largest when the magnet is at 90 degrees to the coil. and no current is produced when the magnet is parallel to the coil. As the magnet rotates, this cycle repeats. So mains electricity is an alternating current. This means that the current changes direction continuously. In the UK, the mains electricity changes direction 50 times a second, so we say it has a frequency of 50 Hz. Now pause the video and complete task 2. Let's check our answers to task 2. First we have to fill in the blanks. In an alternating current, the flow of current repeatedly changes direction. AC is created when rotating magnets are used to produce electricity. This is because the north and south poles cause the current to move in opposite directions. This is the method used to produce electricity in power stations. Therefore, the mains current is AC. So the missing words are alternating, direction, magnets, opposite, and power station. What is the frequency of the UK mains? It's 50 Hz. We can represent the flow of electricity on a graph. These are voltage time graphs. The graph on the left is showing us a direct current, and you can see that the voltage is consistent with time. But the graph on the right is showing us an alternating current, and we can see that the voltage changes direction over time. It passes the 0 point, which means that it's flowing backwards. The UK mains has a frequency of 50 Hz. This means that it changes direction 50 times every second. The peak voltage is 330 volts. But since it makes little difference to us whether the current is flowing forward or backward, we can treat all of the current as if it is going forward, and then calculate the average voltage. We call this the root mean squared voltage, the RMS voltage, and that is 230 volts. So we say in the UK that the mains voltage is 230 volts, despite the fact that the peak voltage is 330 volts. Now pause the video and complete task 3. Let's check the answers to task 3. First, we have to label the peak voltage, which is 330 volts. Then we have to label the RMS voltage, which is 230 volts. Explain why the mean voltage of the UK is not 0. The direction of the current flow does not affect the amount of energy supplied. We work out the mean voltage, treating all the negative parts of the graph as if they were positive. This raises the mean value to 230 volts. Now let's look how AC current is represented on an oscilloscope screen. The oscilloscope can be used to study the change of electricity over time. Its screen will show us voltage on the y-axis and time on the x-axis. Let's look at some examples of how to read off an oscilloscope. We're given two pieces of information. The time base of each division is 0.25 and the voltage division is 4 volts. This means that every square across represents 0.25 seconds and every square up represents 4 volts. So the first thing I'm asked for is the maximum voltage. So to find the maximum voltage, I can create a scale knowing that every square is worth 4 volts. And then I need to mark off where the maximum voltage is. And I can read across that the maximum voltage is 8 volts. The time period is a little bit more difficult because what I need to do is to measure how long it takes for one wave to be created. So I know that the time base is 0.25, which means that every square is worth 0.25 seconds. So now I can mark off how long one wave is, and I'm interested in looking from the start of that wave to the end of that wave. How long does it take for that wave to be created? Well, it looks like it takes 1 second. So I can fill in my time period as 1 second. Now the frequency is how many waves there are in a second. And I can find that out by doing 1 divided by the time period. So my time period here was 1 second, so I'm just doing 1 divided by 1, which equals 1 Hertz. Let's have a look at the second example. In the second example, we've got a time base this time of 1 second, so each square across is worth 1 second, and a voltage division of 2 volts, so each square up is going to be worth 2 volts. So to find the maximum voltage, I can put in my scale on the y-axis, and I can mark off again where the peak voltage is found. And reading across, I can see that the maximum voltage this time is 8 volts. Now this time my time base is 1 second, so each square across is worth 1 second, which means I can measure from the start to the end of my wave, and this means that I have 8 complete squares. So 8 complete squares with one square being worth 1 second tells me that the time period is 8 seconds. If I want the frequency this time, I've got to do the 1 divided by the time period. Time period is 8 this time, so I'm doing 1 divided by 8, which gives me 0.125 Hertz. Pause the video and complete task 4. Let's check our answers to task 4. For the first graph, the voltage should have been 2 volts, the time period is 1 second, and the frequency is 1 Hertz. The second graph, we have 9 volts as the maximum voltage, 2 seconds as the time period, and 0.5 Hertz as the frequency. For the third graph, we have 16 volts, 12 seconds is the time period, and 0.083 Hertz is the frequency. And for the last graph, we have 4.5 volts as the maximum voltage, 1 second as the time period, and the frequency is 1 Hertz.